Welcome, everybody. I'm Tim Mayer.
Hi, I'm Biplov.
We had the fortune of working on this chapter. It was a really great opportunity to explore different deep learning methodologies. And we have a very unique real-world use case for this semantic segmentation around crop mapping. And at the outset of this workflow, we wanted to talk about the why of this chapter and how this effort really sort of came into fruition. The work itself around this semantic segmentation really bore out of this effort that's highlighted in the chapter in the Kingdom of Bhutan. And I'll skip forward one slide actually, and then go back. There was an effort several years ago around advancing science, technology, engineering, and math in Bhutan, and this was through the NASA Capacity Building Program. This was a joint effort from NASA and funded also through the State Department to help collaborate and work with practitioners in Bhutan, and this also surrounded efforts with students in Bhutan, and a lot of our colleagues collaborated with practitioners in Bhutan, specifically the folks who are working in agriculture, and we were able to explore and do a series of trainings in Bhutan. And there's a paper that came out of this that leverages classical machine learning approaches to help improve and integrate Earth observations into their efforts for mapping crops, especially key crops for export and also for just livelihoods within the country as well. So this classical machine learning approach was relatively straightforward, and we really designed this to be adopted for the practitioners in Bhutan. And this system is called ACES, and you'll hear that over and over again. It's Agriculture Classification Estimation System. Or service, excuse me. And this is you can refer to this paper. This is a good resource for sort of the overall concept of where this chapter came about. And if I slide back one here, we were able to go and sort of launch this effort in Bhutan in 2023. And there's some articles that we'll link as well about sort of the integration of this work and the trainings that were involved with it as well. So this was a long-term collaboration. But all that to be said, there was obviously next steps that came out of that work, and some of it was surrounding improving some of those agriculture classification maps, and that led to Biplov and I working on developing software packages. So there's another package that's listed here, which is the servir-aces package, which is really around deep learning methodologies, which you'll use in this chapter. And then there's a paper which we refer to as well, and a lot of the methodologies overall in this notebook is referred to in this paper, and really sort of what we identified. And feel free to read through it. It's a nice read relative in complement to the notebook, is leveraging a variety of deep learning methodologies to better estimate crops, so specifically around rice. So this is a good hands-on exercise that you'll walk through, and you get to explore two different methodologies, and you also get to leverage higher resolution that was originally utilized in the machine learning approach for ACES. So this is using planet imagery as well. So there's a couple additional elements that we laddered off of from the original work. And I think this is a good opportunity now, if you're moving through the book, to go to the website, and then you can find our chapter here on semantic segmentation, and you can go ahead and launch the notebook right from the web page. And I'll hand it over to Biplov.
Thanks, Tim. Okay, so I'm gonna walk you through the chapter itself, the notebook, and explain different components of the notebook, how the notebook is designed, and also how that links to the package that Tim mentioned earlier. So let me share my screen here. Okay, so this is the main repo of the book that we're currently working on. And there's also the website here that we've built around using the Quarto, and it hosts all the chapters, everything. You can find the notebook and everything from this website, which is linked from that GitHub page that I just showed. And the chapter we're looking here is the semantic segmentation on crop mapping. Again, this is basically the uh, same notebook, has like everything over here, so you can nicely see without having to run. It lists all the outputs of each of this cell. Um, but you can also go and actually start running this notebook yourself in Colab. Uh, you can like download it, use it for your purpose. It's all open source. You can do whatever you like with the package or with the notebook. So I'm just gonna click run on Colab, and that will take me to the actual notebook that now, if you're following along, you can also start just working with this notebook.
Yeah, I think one thing we should mention at the outset is when you're launching these notebooks from the book website, you can do a copy of the notebook as well, and that way you're not making edits to the original notebook. And that's just a nuance of the Colab itself. But basically, for all these changes that you'd be doing to the notebook, it just wants to iterate, are you actually saving this? Partly it's because we're the owners, but just it's good practice when you're launching these notebooks to take a copy. That way you can sort of treat it as your own and make changes more readily.
Yeah, this makes sure like you're making a copy in your drive and open that copy, so you could see all the changes once you run through the notebook. Just a brief overview on the contents that we have here. We have prepared many of the data sets as well as the models, because it's going to take some time if you're following along. We just want to give you a sort of the feel what you'll get at the end of the running the modeling effort and how you could use it. But we've already prepared all the data sets as well as the model that you need to run this notebook. So we'll set up some of the environments, we'll download the data sets that we have prepared. We have a config file that basically manages all your environment, that manages all the settings that you need within the deep learning framework that you can provide externally without having to go through and tinker at the code level. You can update that, and then we'll run two model. We'll run a U-Net, which is a patch-based model, which is an image, a pixel-based patch-based model, and a DNN model, which is more of a point-based model. U-Net would help you to capture some of the topological relationships, some of the semantic relationship, while DNN would be at the pixel level. So you get the properties of the pixel at different sample points. We'll also show like how sampling is done here. After we train the model, we'll save them and we'll do some inference using that model on the newer data sets or on the newer paths. And then we'll also do some independent validation. We've collected several data points using Collect Earth Online to capture these independent data sets, and these data sets were captured by not by us, not by the people who developed the model, but by some of our collaborators from collaborators like partners and other folks who worked with us during this project. So we'll use those independently collected data sets to see how well the model is performing. And finally, we'll just see like all the plots and figures to get an understanding of like how different kind of things went through the modeling effort.
And I would
okay.
I would add in one element too that you mentioned about the different models. Part of the rationale too is when we first did the effort around the original ACES work using the random forest, which is pixel-wise classification. There's a really neat, unique feature of Bhutan. It has a lot of elevation. It's a lot of topography. And the rice, both upland and lowland rice, was a major sort of challenge for that model. So part of the exploration was bringing in a patch-based modeling approach, this U-Net model, and exploring also just a DNN. So there's a lot of rationale as to why we wanted to explore these two different methodologies based off of the limitations associated with just a pixel-wise classification, pixel-based classification, due to the extreme topography and also the cultivation practices in Bhutan. So we wanted to definitely highlight there's some value in sort of exploring the different benefits and trade-offs of these algorithms in this real-world instance. Back to you, Biplov.
Yeah, thank you, Tim. Yeah, that's a really important point. And something also to add on that is that we actually also, so I can share the paper here itself, we actually also did some feature engineering and played around with the combination of different features. We're using Planet images for the modeling effort. So we used the NICFIP mosaic RGBN channel from the Planet. As Tim had mentioned, there's like a lot of elevation variation within Bhutan. We also used combine the RGBN with the elevation. We also bought in Sentinel-1 images with the RGBN, and then elevation Sentinel and RGBN channel. And from the set of experiments we conducted, we found that the U-Net was performing much better. And on the U-Net, the variation of including the elevation, there's like less than 1% improvement without using them, but you still see some benefit. And this was, again, I have to say, like a very data sparse region. Here's one picture here, like a lot of cloud cover going on during the monsoon season. During the monsoon season, it's a monsoon-fed growing area. So, a rationale for using the Planet was instead of just Sentinel-2 was because there's a lot of cloud cover, and we wanted to capture as much of the information as possible. So it would also give you some practicality when you are working with any kind of this problem on what things to consider when you are designing your experiment and when you are working with deep learning models. Okay, cool. So let's now run through the notebook. So before we run through the notebook, we want to make sure that we're connected to a GPU instance here. So if you go to your change run type, you can see there's a freely available T4 GPU, which you can select and then connect T4. Once you've done that, we also want to go and click on change run type, and we want to select a little bit older version here. I've already selected it because this library depends on some of the older TensorFlow version. So we want to go and make sure you selected the older version. So this is at the time of recording. We have 2025 7 July available. So we'll select that. So now you've made those changes. Now we'll go and run this. Again, all the data sets, everything would be storing in Google Drive. That would be much easier for us to handle it through the web platform. So here I'm just importing the Google Drive API and making sure that it's on the needed path. Just gonna hit run. And it will ask the permission to connect to the node, to the Google Drive. Okay, so it says it's mounted at the content drive. So your content is right over here, and you could see the drive folder here, and these are your Google Drive and your shared drive, and making sure that the your Google Drive is mounted and it's ready to go. The servir-aces package is available through PyP, so just hit the pip install servir-aces to get that package in, and then make sure that it's available for us to run here.
And that's the Journal of Open Software Science. Feel free to check that out as well. There's a lot of documentation on a variety of other models as well. So this is using, you can access the U-Net and the DNN, and there's a lot of statistical approaches and other models in there as well. So if you're exploring future efforts and you want to sort of roll out different architectures, that's a good package to look out for. And again, refer to that publication.
Yeah. Okay, so now we'll also clone the main repo here, and I'll talk about why we're doing that in a bit here. But basically want to make sure that all the config and everything is available. So that will also come here in your content. We had drive that we mounted earlier. Now you'll see a new folder called servir-aces. The next step is downloading the data sets. As I mentioned, it takes some time for if you're wanting to prepare your own data sets, but we've already provided those data sets. There's another notebook here which is linked to this notebook that basically walks you through how you can use use this notebook to basically produce your train, test, and validation data sets. You train your model on the training data sets, use the validation to make sure the model is improved, and then the test data set is kept aside, and you test your after all the iteration of the modeling is done, then you'll bring in the test data sets and make sure that your model is performing as you want it to be.
And to
so
that
I'll
point, if you're at the very beginning of your workflow and you've got a problem set, start with that notebook that Biplov had mentioned, because that will allow you to generate a training data that's ready for deep learning workflows. So even though we're going through this workflow right now, start at that other notebook if you're at square one of a totally novel research question. And that'll be a great place to sort of generate those different training data.
Yeah, it has like all the config that you can use and start basically generate your PATS data sets or point-based data sets for your U-Net and DNN model respectively. Okay, now going back to our original notebook here, I'm just making a new directory again. Okay, here inside the content, there is a data sets that's created. So provided these data sets from a Google Cloud storage bucket. So we'll just go ahead and copy those into our data sets. So yeah, here you can see we have like different images. These are tiled together. It's copying all the data sets. It's also copying the models. Model has already been trained, saved, and those checkpoints are provided here. It's doing same thing for the DNN as well as the U-Net model. So it will take some time to copy and put that in your content datasets folder here. Just give it some time.
Yeah, this might be a good space to talk about the data sets itself. I know there's maybe a section down below, but as Biplov had mentioned, there is a bit of feature engineering that's happening, and there's the planet imagery itself, and also Sentinel-1, or excuse me, Sentinel-2. So all of those images that were used in the training, and for this example in particular, are already staged in this this Google Cloud platform bucket. So for your workflow overall, you won't necessarily, if you're starting fresh, you won't have this data stored in a bucket. But for this active workflow, just go ahead and let it run, and you can then investigate this data if you wanted to, and sort of see the tart up or the zipped up images here as well.
Yeah, and to that point, I'll also say that, and I'll just share this paper again. We also experimented including some of the indices and without including some of those indices. So indices being, your NDVI, your EVI, all those things that you could derive from the planet imagery. So we did a experiment on including those indices and without including, and we found that there's very small differences with not including them. So here, if you are looking at the precision recall or F1 score, we found that there's like maybe 1% or less than 1% difference. And during this becomes particularly important because during the inference, if you're using like GCP or Earth Engine, at least at the time we were using Earth Engine, and there's some limitation on how much of the payload could be transferred, and that gets like really buggy and may not be a very smooth experience. So we were mostly developing it for the online inference purpose. That's why we decided not to include these indices for our application. Again, feel free to experiment with this. But if you're doing, batch inference, if online low latency is not something that you're looking to do, in those cases, you can also train a model by including indices. Just that your feature or your parameter set probably would get much larger in that case.
Yeah, and I think also at the high level here, a lot of intentionality and thought was put into these indices and relating that to the crop itself and sort of the phenology. But after all of this modeling, we didn't necessarily see a massive improvement with this considerable feature engineering that's included. So something that we would mention in the outset as folks are moving from classical machine learning, where feature engineering is really important for the algorithm at hand. These deep learning approaches didn't necessarily lead to better outcomes with additional feature engineering. So in some ways, we're sort of advocating that you're removing a step and still getting the benefit. But we just want to put that caution out there that it's only relevant for your use case at hand. But in this case, the algorithm was able to perform almost the same with all the feature engineering. So we're also sort of advocating here that the excessive amount of feature engineering and all the work that goes into that isn't absolutely necessary for this use case. So that's a real benefit to this workflow, and also an interesting aside for these architectures.
Yeah, and again, just emphasizing, it's very use case dependent.
Yes.
One thing I'll also point is that we didn't iteratively, for example, just put in NDVI and exclude all other indices and see the performance, include NDVI, EVI, and remove all other indices and do the experiment. We didn't do that. So there might be a combination of indices that would perform much better than with including all of them. So there's also some limitations around that, which is also explained here in the paper. Okay, so it looks like everything is downloaded here. Now you could see, all the images. You could see the model themselves. You could see the prediction, which will come back to it in a bit here. All the training data sets. Everything is loaded now here. So now next thing we'll do is we'll start create a config file variable. We saw that our repo was downloaded earlier, and if I could look inside here, okay, I don't see the environment file. I think that's because it's a hidden file, so probably have to just run this. This is doing, it's there's a env file which you can actually see when you go to the GitHub repo. So let me open up that quickly. Here you could see this .env example file that has like all the settings that you can use for your notebook for running this model. And here we're basically making a copy of that. So now we have the config.env file, which you should be able to see right now here. So next thing is basically changing your base directory and your output directory. This the base directory is from where you're running. What's the base path that other paths should be constructed from, and what's the output directory. So I'm just gonna copy this here. And next is making sure the output directory is correct. Okay. Once that's done, we'll also need to specify the data directory that would be used. And these are again coming out of the earlier notebook that we didn't went through, but we just downloaded the data from. Okay, so now the next step is, again, we're not using any elevation or Sentinel-1 for this use case because we haven't prepared the data sets for this particular example, for this particular notebook. But if you have, just go ahead and enable, put them to true for whichever data sets you've exported. Okay, so let me go and find the here. Okay, so it's already false, so I'm not gonna change anything there. The path size, the default here in the environment file is 128, so I'm gonna change that to 256 by 256 because that's the image paths that we have here. 256.
And that again that's generated from that other notebook that you're welcome to walk through, and that's where the patches are actually created. And these are 256 by 256, and this is the planet imagery and also the Sentinel-1 imagery. So that's actually the patch dimensions, and that's relevant. We'd also recommend reading through the U-Net paper that we'll link as well as a sort of a standard architecture, and those patch dimensions for when it actually does the encoding and decoding through the U-Net itself. So that's really about the size of the patches themselves.
Yep, that's a good point. Yeah. So once you've done that, the other variables, other config that you want to play around is with this training size, testing size, and validation size. These are very specific to this data sets that we have here, and these were pre-computed. Again, there's another notebook that tells you more about how you could calculate these sizes of the data sets. I'm not gonna go over that notebook. It's been already pre-calculated, so I'm just gonna make sure that that number is represented here. Looks like we already have that number here in place. It's also asking us to change the batch size. If you're using larger batch size, you might run into memory issue within the Colab environment. But if you're running this locally, or if you're running on a high-end compute infrastructure, you can increase that, and you basically can experiment with different numbers until you hit that memory limit. The other thing is the epoch. It's saying we can change that to 30. One thing I just realized is that we don't have to like manually go and change this. There's like this nice little text box that you can use to basically make changes. As you can see, we had already changed our base directory, data directory, all these things. But if you haven't, you can also just go ahead and use this text box to make changes to them. Looks like all of our things, all the settings that we wanted to change are already correct here. So I'm just gonna hit run for this one.
I'm glad that you walked through that, working through that environmental file though, because that'll really enable folks to use this and explore anything they want beyond just using this sort of GUI approach here. So you can really just launch that environmental file by itself and then make all the changes you want and save those independently too.
Yeah, exactly. Yeah. So the way it work here is it will take all the values from this text box and create a dictionary, which will then be used to update our config file. Okay, so now that our config file is updated, and we can go and open that again to make sure everything's are reflected here. If you remember from before, I hadn't changed. I think I didn't change like epochs, other things, and now it's changed over here. Okay,
Yeah,
so we have
557. You changed the patch size, so it's reflected there. Perfect.
Yeah, so now we have made the changes on the config file. The next step is basically running the model. In this one, we'll focus on running the U-Net model. There's also an example on how you could run the DNN model, but let's start with the U-Net model. So within the, if you remember, we had already installed the servir-aces package, and it's available for us to use. So the aces is that particular package that we installed above, and it has a bunch of different classes that you can use to make your training with this deep learning model easier. So we're just importing them here at first. Okay, so this config class has it takes in your config file, and it basically sets up those configuration that we provided earlier. So I'm just initializing that here. If the checks the data directory is there, the model directory doesn't exist. If it doesn't, then it will create one. Now, most of our config are available in this config.env, and we can go and check for those here. Next, we'll load our model trainer class. The model trainer class helps us train the model. It would configure the memory growth, creates these TensorFlow data sets for training, testing, validation, builds and compile the model, as well as prepare the output directory and start training and save the model there. It also does the evaluation and prints the evaluation metrics and saves all the parameters, plots, and models. So this is a helpful class that we can use. We'll just initialize that. Next, our task is to now train and save this U-Net model. So as I mentioned before, these are all the things that you can do with this model trainer class. There's a train_model function that will help you do all this. So we'll just go ahead and start training the model. It will take some time if you're following along for the model to train. It will just start the training process and prints out relevant information here. You can also see some examples of input, which is a batch size of 32 as we specified before here, the batch size of 32 to 56 by 256 batch size, and total number of 8 features. You can see all the values. These are all normalized between 0 and 1. And then if you go down below, you can also see the output values. So we have 5 classes here with a batch size of 32 and a batch size of 256 by 256. Similarly, few more examples from validation datasets and the testing datasets, and the simple U-Net model that we've initialized here that provides you the model structure, all the layers within the model, total number of parameters here. Now it's starting to train this model. So as you can see, it takes quite a bit time here. So we'll just let it run for some time and then we'll come back to this later on. Okay, so now we can see this model has finished training. It run this epoch all the way through, run the validation data sets here, spit out some of the metrics that I might be interested in. It saved all the parameters and model config and objects there, as well as it's printing some of the training loss, validation loss, and several other metrics, as you can see here. Okay, so now we've done that, we will save this config file, which I've already saved here. So we could come back later if we're doing different experiments and seeing which combination of parameters makes sense. So we'll need for that purpose. So we're saving those environment file here. And then next we'll load these log files that we have saved in a TensorBoard. It gives you a nice way to visualize them. And you can visualize this right here in the Colab notebook too. Okay, so now we can see all the values through each of these epochs here. Loss, precision, recall, all those kind of things. If you wanna play with this, also provide the link to TensorBoard documentation in the description. You can go and play with them. So now we have saved the model. Next we'll go and load that model. Yeah, so I'm here basically printing what this model looks like. Next we'll do the inference. For inference, you need to prepare your prediction image. Again, there is another notebook that you can go and look, but for this purpose, we've already done the inferencing through that notebook. In the similar way, if I go to the table of content here, there are also DNN model, which runs in basically similar way as we run our U-Net model, loading the model trainer class, and then doing .train_model function within that. So for this one, I'm gonna skip the DNN modeling effort. And next we have some ways how you can incorporate some of the independent validation within your data sets, within your modeling effort. So for this, we have few data points collected using Collect.Online by some of our interns who worked with us during that time. And these are all provided again through the Google Cloud Storage bucket, which you can again look at up. So here again, importing all the Earth Engine G map environment, and here I've already exported the output from the U-Net, which you can see here in the map too. In the similar way, you can also see the output of DNN model. You can also calculate the error metrics, false positive, false negative, all those kind of things, and some of the figures of training and validation plot could also be plotted here. So this notebook would provide you many of these examples on how you could train a model, save various artifacts coming out of that model, plot some of the things on training and validation stats that you want to see, as well as run the inference, prepare your image and run the inference through the saved notebook. So I hope this lesson was helpful. Thank you for staying until then, and we'll see you on our other data lessons in this deep learning book. Thank you.